Our next talk is by David Kunzman. He's a senior PhD student on the verge of graduation. I think he's a few weeks away from his defense. So yeah, grill him. This is going to be his thesis work. And if you've got a big pot of gold giving him a job offer, I guess that'll be welcome too.
Oh, I got one of those already. Oh, I actually have here. All right, so yeah, so I'm getting pretty close to my thesis defense, so I'm going to just apologize ahead of time. I didn't spend a whole lot of time on these slides if they're not as fluid as they could be. So I'm going to talk to you today about runtime system support for heterogeneous systems. This is a topic I actually talked about, I think, 2 charm workshops ago in the context of the cell processor and using different host cores across, or in a single application using SPEs and PPEs in the cell processor. We've done some work in updating this for including support for GPGPUs, so that's what I'm going to talk to you about today. So first, just setting up the context of why we might want to do this. I don't think this is particularly mysterious to anyone in this room, but I'll say it anyway. If we look at some of the more recent host core architectures or host processor architectures, compare them against some of the various accelerator technologies that exist today. So NVIDIA-based GPUs, even the cell processor that was released back in 2008, that you can get speed ups if you make use of these specialized hardware architectures. And we see these becoming more and more commonplace as time goes on in a variety of settings, workstations, even a gaming console, the PlayStation 3, and the data here for the top 500 and grade 500 numbers, I think is about 10 months old at this point. But several of the top clusters in the world are making use of a lot of these accelerator technologies, and thus have heterogeneity in them. So what's the problem? So the problem really stems from being able to efficiently make use of these things. So being able to program them is challenging for a variety of reasons, including one, you need to include architecture-specific code into your application. And I mean this both in the sense that you have to make API calls mixed in your application, and that it's mixed in the application for performance reasons. But in a lot of cases, you also have to change the structure of your application to fit the execution model of the hardware. So for example, GPGPUs run in a SIMD-style manner. Cells, you tend to focus a bit more on streaming data through the accelerator cores and so forth. Mike's even a little bit different. There's also other things that the program has to include, including to accommodate for, which, for example, the division of address spaces, which is not so much the case anymore with some of the more modern GPUs, but in some cases you still need to do this. So the programmer has to include explicit data movement in their application that they otherwise have to compile out if they're running on host cores. There's a lot of other questions too, so how do you divide the work up between the various cores, host versus accelerator? So how do you load balance your workload across these things? And various effects relating to the non-pure nature of the cores. So, for example, if on a cell processor, if you slow down the PPE, you're going to slow down all of the related SPEs because they rely heavily on the PPE being very reactive to their needs. Less so the case for GPGPUs, but in the same vein, you have to make sure you're paying attention to the GPGPU to keep it busy. All right, so with that in mind, we're including, we're working on including support for these accelerators into Charm++, and the figure here is basically a high-level overview of where this fits in the sort of entire Charm ecosystem. So at the very top, you see several programming abstractions, and these have been included into Charm++ for a variety of reasons. The very top one is charge, so it's basically a way of making charge is a way of making programming in Charm++ a bit easier. It gets compiled. So it's an effort to actually have a compile-based language based on Charm++, and then a variety of other things. I won't go in and explain each one of them, but I'll in particular point out accelerated entry methods because that forms the basis of this work. The general idea is then you take all of these programming model abstractions, with the idea that they can be interoperable. So you can use one abstraction for part of your application and another abstraction for another part of your application. You map them down onto a common substrate. In this case, the common substrate is the Charm++ runtime system mixed with the general ideas of over decomposition, so on and so forth, embodied inside the Charm++ programming model. From there, once you have your application mapped to this common substrate, excuse me, the runtime system at runtime takes over the scheduler and various components inside the runtime system. For example, the load balancing framework or the fault tolerance framework will take care of various things on the programmer's behalf as the application executes. And what we're doing here is we're adding an Accelerator Manager to facilitate the use of facilitate the use of accelerators. And on the very bottom is the hardware, and the hardware that all of this work gets mapped to. Like I said, the basis of this work is accelerated entry methods. So inside of Charm++, a Charm++ application is basically broken down into a large set of tasks, where each task is embodied inside of an entry method, and that entry method is associated with a char object. So it's like, you can think of it as the location or the data associated with executing that task. And there's a variety of these entry methods inside of Charm++, threaded entry methods, expedited entry methods, the list goes on. We're adding another one called accelerated entry methods. And the general idea is that an accelerated entry method is intended for the compute-intensive portions of your application. The semantics of it is that you take a regular entry method, you break it into two. Inside the function body of that entry method, you place all of the very compute-intensive code, but you remove system calls and stuff like that, things that generally cannot run on accelerators, printfs, system calls, other entry method invocations. You simply take that code and you move it into the callback function. So it's really just a two-stage entry method. So the way the runtime system is going to make use of these things is if we have a where's that laser pointer? So in section 1 up here, you can think of it, like I said, you can think of a Charm++ application as a series of tasks, and those tasks are invoked via messages being passed between the tasks. And those messages express the data dependencies in the application. So you can imagine the Charm program, the Charm++ program, really is a DAG of executing tasks, with the messages being the edges of this DAG. So the idea is that the programmer will apply our abstraction of accelerated entry methods, AEMs, to their application when appropriate. So maybe some subset of these entry methods will actually be mapped over to accelerated entry methods, as shown by the colors here. And then at runtime, depending on what hardware is available, the runtime system might do different things. So for example, if you run on the host, it's going to behave exactly the same way as it did before. If you run on a cell processor, the runtime system is going to use the entry methods as sort of chunks of work, and it's going to begin streaming those chunks of work through an available SPE or SPEs. In the case of a GPU, you're going to start. The runtime system might instead take like entry methods, so entry methods that are essentially running the same code, and agglomerate them together to form sets or batches, and then execute those batches as kernels on the hardware itself. In cases where maybe there's only one or two, or they're not well suited for the GPU, something like that, maybe it'll execute it on the host instead. So all of this happens dynamically at runtime. So there's several features. I won't go into detail for the sake of time, since we're short on time. Just really quickly, so entry methods you can apply a variety of things to them. So for example, you can do triggered entry methods, which really is just a hint to the runtime system, saying that the accelerated entry methods on those objects are going to execute in a one-to-one basis. So basically it gives the runtime system the ability to do a little bit of counting and save some time in trying to predict when, like, the last accelerated entry method in a batch is ready, something along these lines. Splittable is a way of essentially, you can think of it as taking an accelerated entry method and applying something like TBB or OpenMP to it. So you're going to take a single entry method and you're going to break it up into a whole bunch of splits, and those splits run concurrently with one another. And that this is a way of breaking apart the pre-existing requirement that there's a one message per one task requirement. Now you can actually have multiple tasks spawn from a single message arriving at a processor. We've also added support for shared and persistent parameters inside of these things. So shared just is a way of letting different instances of the same entry method actually share the same data buffers. So you can reduce the memory footprint when moving data back and forth between devices. Persistent is a way of letting the runtime system know that data can actually stay on the device itself between invocations to a particular entry method. And I won't, like I said, I won't go into details of how these things work for now for the sake of time. Just to give you an idea of what these look like. So here's a accelerated entry method called doCalculation that is both triggered and splittable. The key idea here really is, in this example, is splittable. So actually, starting from the top, there's no pass parameters. So the way you would invoke this function is just object.doCalculation with no parameters. So the same way you would invoke a standard entry method. In addition to the pass parameters, we also include local parameters. So these are just the object. So this is, think of the implied object as this pointer. That you're just telling it which member variables it's going to access, and this really stems from the fact that we don't have a compiler that can do the analysis on this function body. So you're just telling it what mode the various pieces of data are going to be accessed, so it can do optimizations at runtime, not transfer quite so much data, or reduce mem copies. The splittable, essentially this is a stencil tile for a two-dimensional tile. So what this code is saying is, give me a split, or think of it, give me a concurrent thread for every single row. And then, so this first loop is just, depending on which split you are, looping through the rows that are assigned to you. So it's worth noting that the runtime system may give you num rows threads to execute this entry method. It might give you one. It might give you something in between. So we do leave it to the programmer to handle the case of anywhere between 1 and however many specified splits there are. But otherwise, the code looks fairly similar. So this is a Y loop over the tile. This is the X loop over the tile. And then you would just fill in whatever the tile calculation is. In this case, some stencil calculation with a max error calculation. Then in addition to the accelerator, so that's the basis of the unified programming model. There's probably a lot of improvements that can be made, but for now that this serves our purposes, when I mentioned TBB and OpenMP before, the idea is that maybe in the future we can extend this expression to be a bit more generic, like OpenMP. You can specify like this variable's a reduction, or TBB to break this up a little bit nicer. But so for the time being, this is what we have. Okay, so moving into the runtime system itself, there's a component in the runtime system called the Accelerator Manager, and it has a variety of duties. I'm just listing two of the basic duties here. So the first one is to collect performance data, in particular in relation to the accelerator, and then to try and match that up with the execution of the application to see if the application's speeding up and how much work are we dividing between the host and the accelerator cores. In addition, there's also load balancing strategies. So in Charm++, there's a pre-existing load balancing framework. This is actually separate from that. So this is a local load balancer that is simply shifting invocations of the accelerated entry methods between the host and the accelerator device in an effort to optimize the performance, so to reduce execution time. Okay, so with these strategies in mind, so what the runtime system is, what these strategies are doing basically at runtime is we're considering both the host core and the accelerator core. So this line here, so the x-axis is the percent of work being shifted to the device, with 100% on the left and 0% on the right. So just the blue line represents how much time the accelerator is taking to execute a given workload. So if the accelerator has all of the workload, it's going to take some amount of time to execute. And as you reduce the percentage of that overall workload on the device, its execution time goes down. Vice versa, as you decrease the amount on the device, the host starts taking longer and longer. So these various strategies that we've included are simply sort of trying to mimic this graph in an effort to find a sweet spot in that graph where the time to complete the workload across all of the available cores on the node is minimized. We call that S sort of the sweet spot. So that's essentially what they're doing. The graphs on the side just show what the graph would look like if, in this case of B, if the accelerator vastly outweighs the host core in terms of performance, and vice versa if the host is much better, which is application dependent. Okay, so we're going to make some runs. We ran some experiments on Forge. I'll just show you a few of these. Forge really, the takeaway point here is it has 16 x86 based cores per node and 6 accelerator units that are based on Fermi per node. There's actually some nodes now that have 8, but when I ran these, it was 6 per node. So that's the high level. This is the architecture itself. So there's a whole bunch of, I like to call the SMs cores, but there's a whole bunch of these SM units which have 32 cores each, and they execute a single thread of execution in SIMD lockstep manner on those cores, and then they can do the collection of 32 threads is referred to as a warp, and they can do very cheap context switching between warps to high latencies for instructions. We're using this in a manner that we're in such a way that the L1 cache is being used as, the shared memory is being used as an L1 cache as much as possible. And then there's the L2 cache and device memory associated with the device also. Sorry, if you have any questions, feel free to stop me. I'm trying to get through this fast because of time. We set up a simpler molecular dynamics code. This code uses an n-squared algorithm because we wanted simplicity and consistency in the results. There's so much variability going on. This helps us analyze the results, essentially, is the main reason for this. But at the same time, we don't want to have a ton more work. So we choose a problem size that's similar to a commonly used system to benchmark NAMD, which is the APOA1 system. And for NAMD running on about 64 cores, and this running on a cell system with, this just run, it doesn't matter how many cores. For NAMD running on 64 cores, you get about 1,000 objects, or I'm sorry, about 6,000 objects, I think it is, and then ours produces 10,000 objects. So you're not getting a whole lot more parallelism, even though we're using this n-squared algorithm. The parallelism is directly related to the number of objects you have, because that's how many tasks you'll have. So here's the performance numbers that we get on using a variety of nodes. Again, I won't go too far into this. At the single host core, single GPU case, we're running the MD code, and despite the fact that the code is not written to use shared memory, it's not written to use constant memory or texture memory, anything like that. We just make use of the L1 cache, and we let you write basically standard C code inside of the function body. We can reach a peak of almost 25% of the accelerator unit running on a single combination of host core and GPU. If we move down from there and just scale up to 1 node through 6 nodes, we slowly increase. But eventually, we do consistently lose percentage of peak. And this is mainly related to the communication in the application. So I'll just point out we're getting up to, on just 6 nodes of Forge, which is 100 host cores and 36 GPUs, almost 3.5 teraflops of performance out of the application. The time column is the time to execute 128 time steps in the application. Oh, seconds, sorry, yeah. Yeah, so by the time you hit 6, the time steps approximately 54 or 55 milliseconds, something, if I remember correctly. So we look at the 6 case. We open up the 6 case in projections. If you're not familiar with projections, don't worry about it too much. Essentially, You have a row for every single host core GPU combination. And there's two lines, essentially. There's a red line, which shows force computation being done on the host core. The blue line is force computation being done on the accelerator core. And as you can see, there's a lot of time where neither of them are doing a lot of stuff. And that's basically the communication of the program. So the main reason that we're not scaling with this code is the code's, it's a simple code and it doesn't actually scale well in terms of its communication. So we'll probably visit this in the future and see if we can't speed that up some. But so at least I think we're not doing terribly bad. There's another thing to point out too is there's some variability in the kernel times which is helping cause this, and this is still a bit mysterious. So like take PE78 here. One iteration it takes quite a bit of time, another iteration it doesn't, another iteration it takes a lot of time. I've actually gone into the execution to figure out what's where any load balancing is occurring, and no load balancing is occurring between those between those three time steps. So something like data transfer or scheduling, some of the GPUs are being shared here, so maybe there's an interference between the GPUs. So that might be causing a lot of that. So anyway, so that's where we're at. A few other things that we've tried. So we've also tried to, since we have this runtime system that can dynamically adapt to a situation, we also tried seeing what we can do about, say, interference. So in this case, we're going to run 3 instances of the same application. The first instance is going to use 12 host cores and all 6 GPUs on a single node. The other 2 instances are basically going to just use 2 host cores and 2 GPUs each. The set of host cores used for each instance is mutually exclusive, so there's no overlap, no sharing going on. But the GPUs are all shared. So in particular, GPUs 0 and 1 are shared between all of them. And even more so, 2 host cores, in the first instance, 2 host cores are sharing each GPU. So if we execute this, we can just show the effects. So at some point, so this black line is instance A's performance. You just start running the application. At some point, the other instances of the application begin execution. So at first there's a bit of noise, but the load balancers and stuff take care of that and redistribute the object workload, adjust this is one of the percent device values. So it's telling the balance between the host and the accelerator device for one host core and device pairing. So you can see that the runtime system is allowing the application to adapt to these interference. So this might be particularly useful on things like workstations where the resources are shared. This is the same data. This is essentially all of the percent device value. Well, let me start up here. So this is essentially like every PE kind of has a row. It's kind of blurry, but the color indicates how many objects are allocated to that PE. So at first, everything's basically similar. Eventually, the interference begins, at which point the GPUs that are shared between the other applications become overloaded. The work gets shifted. Those become dark, indicating lower object counts. The other ones become lighter, indicating the objects were moved from the shared GPUs to the exclusive GPUs. Eventually, the interference stops and things go back to normal. So the runtime system just sort of adapts to the environment, making best use of the resources available. The bottom chart is the same idea. It's just the individual percent device values. Again, for time, I'll skip that. Another thing that we recently got working is being able to use memory checkpointing in addition to the accelerator devices. So Charm++ also has fault tolerance support and a variety of schemes. One of the schemes that we've tried so far is memory checkpointing. Other schemes will actually take a little bit of different effort, but for now, this is what we have. So periodically throughout the execution of the application, the runtime system will checkpoint the state of the application, and then as you're running, we actually simulate, as the application is running, we simulate a fault. So that's this huge spike here. So one of the PEs goes away. All of the objects from that PE get failed over to one of the other PEs, as Gangbin described earlier. So the blue line here represents a run without an across host core load balancer. So the performance gets cut in half. essentially because one of the PEs now has twice the work and no load balancing is occurring. The green line, the green plot, includes a load balancer. So the spike occurs. It just so happens the load balancing step happens right after the spike. There might be some time where it's a little bit high until the load balancing kicks in. In this case, it kicked in right away. And then the performance, again, is redistributed and makes best use of the available hardware resources after the fault. Just to summarize real quick, we've been working on adding support for accelerators into Charm++ in addition to supporting heterogeneous systems. Today I talked about our GPGPU support very briefly, but we also have support for cell, and all of this is portable to host core systems as well. We've included in Accelerator Manager various load balancing strategies, support for or integration into other components of Charm++, for example, the load balancer and the memory checkpointing schemes that I talked about. So with that, I will leave it to questions.
So I'm trying to understand how your work relates to what Katish did for Changa. In particular, he had to spend quite a bit of time understanding how much shared memory there was, optimizing the loads of data from the general device memory into shared memory, and
so
I'm not sure how that kind of information can get into your accelerated.
So in terms of shared memory, we're actually using the shared memory as an L1 cache instead. So we're not actually in this regard, we're treating the GPGPUs more like traditional cores than we are GPGPUs with shared memory. In terms of the amount of workload that gets shifted between the cores, we are allowing the runtime system to do that based on measurements, essentially. So when the application starts up, all accelerated entry methods initially are mapped to the GPU, in the case of a GPU. And then over time, based on measurements, how busy the host core is, how busy, it depends on the strategy exactly, on how it does this. But essentially, it's trying to balance the workload between the two cores. And then
but there's a lot of, the CUDA runtime system, for example, sort of does all this scheduling of resources within the GPU. Do you take that into account?
I mean, essentially all we're doing is we're issuing the kernels to the GPU, and that's what it's doing. Right now, in terms of, if you're thinking about, like, say, for example, the register counts per thread or something like that, we have like mechanisms. These things are discoverable, and they're systematic. I mean, the same way a programmer goes about it, testing it. You can launch a kernel. If it fails because of lack of resources, one of your resources is too high, shift the distribution of threads per block or something like that to accommodate that. Right now, the error reporting in CUDA is less than ideal, so that doesn't always work. But that's a CUDA thing more than it is ours. So a lot of these things are auto-discoverable. The shared memory, amount of shared memory per thread goes away simply because we're not using shared memory. We're using it as an L1 cache instead. I'm trying to think of the other resources you might have in mind. Constant memory, we're not making use of. Again, so the big picture. This is really just focusing on the runtime support behind the code and the tasks. In terms of actually optimizing code within the task to make use of, say, constant memory or something like that, you would have to have a compiler sitting on top of it. So we can say, oh, this is a constant at compile time, this is how it's accessed, stuff like that. And that's where something like charge would step in. So then you can start intermixing. You can use the composability of all the various components inside of Charm++. So then charge can optimize, the code, maybe even make different versions from the user code to the generated code for a GPU versus cell versus a host, that kind of stuff.
I think we have just about time.